Can you hear me? Okay. Will you say something so I can see if I can hear you?
Hey, good morning.
Good morning, Christina. How are you?
I'm doing fine. How are you?
I'm pretty good.
We have problem to connect. Hi, Maria, and everybody. We have problem to connect here from the main I don't know room. But we hear you. We are just Daniel, Adrian, and I are here, and we can hear you. We just connected with my laptop.
Okay.
Okay.
Cool. Great.
Cool.
Yeah, it took me a few minutes to connect, but hopefully my connection is okay. Cool. So shall I share my slides and get started?
Yes, Adrian, say yes. You can start on share slide.
Okay. Yeah, so you can see my slides okay?
Yes, perfect.
Great. Yeah, so hi again, everyone. Nice to be back for the second lecture. Yeah, so like I said last time, this one will be focusing on demystifying some of the classic quantum thought experiments that people tend to have heard of in popular science contexts and even in undergraduate courses, but are sometimes not explained in a very clear way, or it seems like something strange going on. And what I want to do is use these tools from quantum computing that you've been learning about and use this to understand these classic quantum thought experiments better. So yeah, hopefully it gives you at least a different perspective on these fundamental ideas in quantum mechanics, and it should also help understand what decoherence in quantum computing is. So there's a nice connection with with the technology side there. So so just recapping the slide from last time, summarizing the lecture series, we had already lecture 1 on the quantum bomb tester and the basics of mapping these quantum thought experiments to quantum circuits. This one is about the more fundamental classic thought experiments, and then in the next one we'll kind of extend beyond to how this connects with other ideas in physics in more exotic thought experiments, I'd say. So yeah, there was a question that Adrian sent me that people asked about experimental implementations, maybe for a classroom setting or undergraduate lab, for doing things like the quantum gates. And one thing which came to mind is there's this YouTube channel called Looking Glass Universe, run by Mithuna Yoganathan, and she did a PhD in quantum computing at Cambridge and then has been making various videos, and she has a few on these quantum experiments at home. So there's this double slit one, and making a quantum computer, kind of using lasers and some crystals to create the basics of the qubits. So yeah, I'm not sure exactly what the components needed were and what the limits of what you can do in those systems are, but I think that they are quite low cost and possible to kind of build yourself. So yeah, I recommend checking out those videos. And yeah, I was also wondering what kind of, I don't know if someone has an idea of what kind of budget you have in mind for low cost, because there are is there any
I think
comment on that?
No, this is exactly what we wanted. The point was, how could high school teachers run some experiments to demonstrate the existence of this kind of phenomena, and then of course, starting from what you showed us last time, is there any chance of actually implementing any kind of quantum gates, either in a lab in high school or in a lab in under computer science undergraduate? But these videos are, I think, exactly what we need, and we're going to watch them and get something out of them. Thank you.
Cool. Because yeah, I mean, I think the next step up is that there are these kits that some companies provide, or that some organizations have made, that are kind of maybe like 2 real qubits, and they tend to be in the thousands. Is kind of maybe £5,000 to £10,000 would be a typical expense for these small qubit devices where you have full control over them. So yeah, that's kind of what I'm aware of, is these. I think this should be much cheaper, a way of building it yourself to show some of the phenomena, and then these full 2 qubit control systems, I think, are a step up in price from there. Cool. So just reviewing last week, if anyone has any more questions from that have arisen since the previous presentation or to do with that, or any feedback from the activities, if you tried them or anything, happy to hear. And I've also been keeping track of a list of some of the topics that came up, that I will collate a list of the relevant papers and things just to guide people towards those resources when I get a chance. So yeah, does anyone have any comments that they'd like to make? Anything else coming from the last session?
One of the links that you had in your slides was the quantum fly trap, and I just wanted to highlight that for all of the other high school teachers. Quantum fly trap was super cool to play around with, and I think high school students would really enjoy a tool like that.
Yeah, thanks for highlighting that. Yeah, it's really good. It really lends itself to, because it's all based on photons, so it lends itself to these kind of interferometer experiments like the bomb tester style, and we'll see some of that today with the double slit as well. So for these ones that really fit into this photon system, it's like drag and drop components. It's made in a really nice graphical user interface. So yeah, it's quite a natural way for someone to get started. And if you don't have the facilities to create your own physical hands-on experiments, it's a very good alternative to be able to play around as though you're in a lab. It really is a kind of virtual lab. So yeah, thanks for highlighting that. Cool. So yeah, any other comments, feel free to let me know, but I'll move on for now. So for today, I'll essentially be trying to get the idea across that a lot of these thought experiments that I've mentioned involve having some kind of measurement. Some observer looks at a quantum system, or there's some detector that detects a quantum system and does a measurement. And the kind of repeated message that you'll see in this lecture is that by modeling those measurement devices or observers as themselves being quantum systems, so taking quantum mechanics to apply at all levels, including to the measurement device, then we can solve a lot of the seeming apparent paradoxes that arise in these thought experiments. And so we'll see that with Schrödinger's cat, the double slit experiment, and some experiments to do with treating observers as quantum. And we'll see these nice connections with decoherence in quantum computing. And I'll also talk about a thought experiment that enables us to test between theories where the measurement devices and the observers can be described by quantum mechanics and theories where they can't be. Because this is whether or not you're allowed to treat a detector as a quantum system is still a controversial issue. It's very debated amongst the community. And so what's really nice about this thought experiment that I'm going to explain is that it actually gives us a way of imagining an experiment to actually distinguish between these two camps that people are on about whether it's essentially this idea of whether a measurement causes a quantum system to have an irreversible collapse into a single state, or whether the measurement device is actually quantum and then keeps this quantumness as it interacts with the system. So we'll see how to distinguish those in a thought experiment. Cool. So we will have these three that I'll focus on: Schrödinger's cat, double slit, many worlds versus Copenhagen test with the quantum observers. And they all, even though they all kind of have this theme of
Hello?
Hello.
Yeah, we to connect, but we are still having.
Hello.
So I think we're waiting for Maria to connect now. Again, I think we lost her. So everybody is still hearing, right? I'm in the hallway. The main computer is dead. But
Yes, we hear you.
but
Yep.
Elmar is actually running his laptop, so I'm outside, and hopefully she'll connect back. Sorry. So far, it's been really good, but I don't know why we are unlucky today. There's also some issues with the networking. They changed the certificates. Okay, so I'm going to go back inside. I'm going to cut my audio, and I'm going to go back inside and let Elmar be in charge of the sound and the video. I'm going to cut my video and also leave the audio, and then go inside and stay with that's our only connection with
Yes, now the microphone is on.
So she also has to leave early. I mean, exactly at 3, which means 2:55. Well, we're not lucky today.
No, there are days like this.
Yeah, sometimes. Yeah. Um, what's the recording?
Sorry. So I unmute you, Adrian?
No, we're good. So then where are we? We're right back to this place, and I'm gonna go. Where was I again? So I don't see her, and I'm gonna go share again. I go back here, at least we're putting this on, and then say we have difficulties. We have, sadly, we have technical difficulties. I don't have audio or video from this computer, but what I'm going to say.
I have audio open for you here.
Oh, I see. How about this?
You want a video?
No, because I have to stay here when she connects. Why don't you tell them from that page, click on the various links and show them what the links take us to.
But I cannot click. I mean, should I share or?
No, okay, I'm sorry. So look, if you say over here, this is an interview with her.
Yeah, so this is an interview that there are links on this page that Adrian shows us, which is our webpage, I think, and then there are links from her.
Right,
Yeah.
so here's what I'm gonna do. I'm gonna play some of these briefly while she's trying to connect. Hopefully she will be able to connect. So now watch, the video is like this.
So Adrian plays a nice video for us.
All right, I'm here with Maria Violaris. Maria, thanks for joining me.
Thanks for inviting me.
Sure thing. So before we get into your research, let's do a little background physics. So what does it mean that the dynamical laws of physics are time reversible? And specifically, what does this mean in the context of quantum physics?
Yeah, so the dynamical laws of physics being reversible is something that we see not just with quantum physics, but also with normal classical physics, with classical mechanics and electromagnetism. Hi, I'm back. Yeah, not sure.
Hi, Maria, welcome back. I don't know if Daniel now has, Adrian, not Daniel. Today maybe Daniel. No, but I don't know if he has a microphone.
I have a microphone.
He has a microphone. Oh, okay. He will connect himself. It's a bit chaos here, so yeah, trapped in fractal.
All right, so please go ahead. I'm sorry that it disconnected. We might still have additional issues, but just let's go ahead as far as we can. So we know that you have to leave right before 3 p.m. because somebody else booked that room. So just let's go with the presentation, and then at the 2:55 your time, we're gonna stop, and that will be it for today. Thank you.
Yeah,
Okay.
I'll try and give a overview summary to fit into the time. So cool. So yeah, the idea, like with last time, is to map each of these thought experiments into a quantum circuit. So you can see what they all look like here. They're quite simple. They're just Hadamard's and C0 gates that we're familiar with, and you'll see the same themes coming up again and again in each thought experiment. They're just kind of configured in a different way because they're representing a different physical situation happening. So let's start with the famous Schrödinger's cat. So this one, yeah, we're gonna represent it by so let me just review the thought experiment to start with. So the idea is that you have a cat inside a box and it's trapped in there with a radioactive atom. So this atom has some probability of decaying, and if it decays, then it will cause a hammer to smash open a vial of poison inside the box, which will kill the cat. If it does not decay, then it won't smash open the poison and the cat will stay alive. And the quantum weirdness is that this atom can be in a superposition of decaying and not decaying. And then if you follow through, if you treat everything in the box quantum mechanically, what that means is when it interacts with the hammer, then the hammer becomes in a superposition of having decayed and not decayed. And then when it interacts with the poison is in a superposition of having smashed open and not smashed open. And then the cat enters this superposition of being alive and dead at the same time, which seems crazy. And that's what Erwin Schrödinger was trying to show by explaining this thought experiment, was to say, look, quantum mechanics is absurd. It leads to cats being dead and alive. And then you have this outside observer that looks inside the box and then somehow collapses the cat's state to either being dead or alive. And so there's this, the standard narrative is that there's this weird conclusion that before we look inside the box, the cat is alive and dead at the same time. When we look inside, it just becomes either alive or dead. And so yeah, there's lots of strange things going on to unpack. There's this idea of, can a cat be alive and dead at the same time, or is it already weird just thinking about what happens inside the box, then there's this idea of the role of the observer here looking inside the box. Like, what do they do to the cat, which then makes it collapse into either being alive or dead? And then there's this idea of why don't we see cats being dead and alive in everyday life if it really is the case that these things are happening? And I see there's a question about why it can't be more direct. The atom decay kills the cat. Why do we need to hammer and poison? Yeah, I mean, you could frame it that way if we thought that one radioactive atom was enough to cause the death of a cat, then there's no reason why you need to add the things in between. We just need the things in between could be anything really. We just need some chain of events where the decaying and not decaying causes the cat to end up alive or dead, and you can put anything you want in between together. And Schrödinger presented it in this way. This is the kind of typical narrative. And yeah, I also, if you see my Qiskit video on this, I used some props to do a little demonstration. And if you're planning to do a demonstration of some kind, then you could take a look at that for inspiration of some props to put together for, it's quite fun for, yeah, giving live presentations. It's nice to have something physical representing the scenario. Cool. So let's map this scenario onto a quantum circuit. So I'm going to have a qubit to represent the atom. And actually, just as the question said, it's kind of illustrated by this circuit. I'm not including the hammer and the poison. I've just skipped them exactly for the reason that we don't really need them to see what's going on. So yeah, in this circuit, I am just having an atom interacting with the cat. So yeah, I have a qubit for the atom, a qubit for the cat, and a qubit for this outside observer that's going to be looking in. And so how can I represent each of these complex objects by a qubit? Well, what I'm doing is I'm saying that all I'm using the qubit to describe is just one aspect of this object. The 0 state means that the atom has not decayed, and the 1 state means that the atom has decayed. With the cat, the 0 state means it's alive, the 1 state means it's dead. With the observer, it's going to begin in the 0 state, which is like a blank memory of the observer before it's looked inside the box. When it opens the box, if it sees the cat alive, then that's going to be stored as a 0 in its memory. So 0 after opening the box means it saw the cat alive. And if it sees the cat dead, then that'll be stored as a 1 in its memory. So the 1 state after opening the box represents the observer having seen the cat dead. So we've mapped these states of each object. We're treating it as a quantum system, which means that we can describe it as a qubit with these 2 quantum states. So are there any questions about that aspect of why I can translate each object in this setting to be a qubit? Okay, so yeah, I'll carry on explaining through this circuit. So everything here is starting in the 0 state. I've not written it explicitly, but that's the idea. And then I prepare my radioactive atom in this superposition of having decayed and not decayed by putting a Hadamard gate. And then now I have this interaction of the atom with the cat. So if the atom is not decayed, the cat needs to, so if the atom is a 0, the cat needs to stay 0, alive. If the atom is 1, so it's decayed, the cat needs to flip to a 1, which means it's dead. And this logic is exactly implemented by a control not gate. So that entangles the states of the atom and the cat. So looking at the overall state vector, we've gone from, we've put this first qubit in the superposition, the other ones have stayed at 0. Then we did this control not, which led to this entangled state being created for the first 2 qubits. So you can see atom 0 means cat alive, atom 1 means cat dead. And so that's that step. So at that stage, the cat is in this entangled superposition of being alive and dead. And now we have this observer looks inside the box. And that measurement, again, we model by another control not gate, because if the cat is alive, 0, the observer sees 0 in their memory. If the cat is dead, that's a 1, the observer sees 1 in their memory. And so you see that just like the cat entered this entangled superposition with the atom, the observer now enters the entangled superposition of the cat, with the cat and the atom. So it's joined in this superposition. And you can, so another interesting comment about treating measurements using control not gates is when the control not gate was first introduced in quantum computing, it was actually called the measurement gate precisely because it has these properties of implementing what we call a measurement by kind of transferring the information in the right logic for a measurement device becoming correlated with the thing that it's measuring. So yeah, and now we can address some of these weird aspects of the thought experiment. So why does an observer only see the cat being alive or dead? Why do observers never see the cat being alive and dead? Well, it's because you can see once it looks at the cat's state, it becomes entangled with the cat. And if it's seen as 0, if it's in the 0 state, it will only see the cat being alive. If it's in the 1 state, it will only see the cat being dead. So it only sees a single outcome of the cat because it's become entangled with the cat when it looked inside the box. So we have this, when we treat the observer as a quantum system, we have an explanation for how it, for what happens when it looks inside the box, why it only sees the cat being alive or dead instead of seeing some kind of weird superposition. And yeah, just included here the code for coding up this circuit in Qiskit. If you know how to do Hadamard CNOTs, then you can build it quite easily. And then you can put measurements at the end to check if it's the state that you expect it to be. Now, there's a more subtle question. So we've put an explanation for why the observer only sees a single outcome. But the more subtle question, I think, about the Schrödinger's cat thought experiment is, why don't we see the so if this cat inside the box is actually quantum, everything inside the box is described by quantum mechanics, then why don't we see things moving like from being in a superposition of alive and dead back to being in just 1 state? Like, why don't we see this whole quantum interactions in the box being reversed? Everything in quantum mechanics can be reversed. Every gate we apply in quantum computing, there's a reverse gate we can apply. So why is this single outcome we see irreversible? I think that's kind of the more interesting, subtle question in Schrödinger's cat. And it relates to this idea of, why do we see our reality seeming kind of classical? Like it seems like on a large scale, macroscopic objects behave as though they're classical. We don't see these quantum effects in general in macroscopic objects. And the explanation for this is decoherence. So we've talked about this system of having the atom, the cat, and the observer, but you're not just an observer in isolation with this box. There's a whole environment around you. And what happens is, when you look inside the box and then you've registered what's inside the box, you've also interacted with all of your environment. So all of the particles around me then get that, once they've interacted with me, then they also join this entangled superposition that I'm in with the cat that I've looked at. And then as all the particles bounce around and they spread out until everything's interacted with each other, you can see that this kind of entanglement will spread into the environment, so that you end up in this whole branch of the quantum state where everything has become entangled with seeing the cat alive, or it's become entangled with seeing the cat dead. So you can see this in the quantum circuit. We can model, let's model each particle of the environment as a qubit. And then this process is like each particle, once it interacts with me, it's like there's a C0 gate transferring that information to that particle. It enters this entangled superposition of me with the cat, with the atom, and this kind of gets passed on through the environment. And so this kind of separates everything into these two separate branches. Is there a comment, or was that? So yeah, there's a question in the chat. So going from quantum to classical, just a lossy compression of possibilities into something like finite. I'm not sure I understand the question. I don't know if you want to clarify.
But what I wanted to this is that I have a video from Vazirani where he describes measurement as being a cascading entanglement with the apparatus. And at some point, that is no longer sustainable, and it collapses into one state or another. So I will have them watch that. But Amy, if you want, you can reformulate your question. You can speak up if you want. Just say it.
I also have a question. My name's Matt Mindock. I'm a high school teacher. And what about if there was cat food inside the box with the cat, or the kitty litter box also inside? And that time had passed. So whether or not the food itself had been eaten would be in this state of being eaten and not being eaten until we've made this measurement as well.
Yeah, so everything inside the box. So let's say if it's before we've made this measurement, then everything inside the box that interacts with the cat would be part of this this superposition where we have the atom and the cat. That would also have so here I'm representing this overall state as like loads of zeros in superposition with loads of ones. And for each of those zeros, you could imagine that it's a different object inside this box. So it could be the 0 is one state of the hammer, the 1 is another state of the hammer. This 0 is one state of the cat food, this 1 is another state of the cat food. And so everything in the box enters that entangled superposition. And then once you observe and you kind of unleash you let the box interact with the surroundings, then that superposition starts spreading out to everything else as well. And yeah, you get these emergent branches where you've got everything either one way or the other way in superposition.
Thank you.
Okay, so I think Amy clarified the question. Is a superposition multiple possibilities vaguely existing at once, or is it just an observation that nothing has yet required it to be a certain specific way? Yeah, so in this way that I've presented it, the superposition is the multiple possibilities all existing in a very physically real way. So we're really saying that the cat, there is a physical branch of the universe where the cat is dead. Stuff is happening in that branch where people are responding to the cat being dead. And there's another branch where people are going about their lives with the cat being alive. And these are both physically existing. So they're not, not kind of vague. They're like the real world that we're talking in right now. Under this interpretation, if this is right, then there's lots of other versions of this world where people are interacting just like us, and other things have happened because of quantum effects having caused other branches of the universe to emerge. So this is why this explanation for measurement is, well, at least one version of it is called the many worlds interpretation of quantum mechanics, because it leads to these many worlds this kind of multiverse of physical events happening in parallel in this superposition. So yeah, in this way that I've presented it, there's nothing special about the observer opening the box. It's just another interaction of the things inside the box with stuff outside the box. There's nothing particularly special about that observation. It's just everything, you just treat it as once it interacts with some system in superposition, it enters that entanglement. And yeah, so seeing measurement in this way almost makes observers not be so special as they might be presented in some explanations for quantum mechanics, because they're saying there's nothing like weird about observers in particular as opposed to any other object in the universe. We just describe them all by quantum mechanics, and they all behave in this way if we model them with quantum mechanics, and then through this decoherence mechanism we can explain why we only observe single cats being alive or dead, why we don't see these kind of quantum interference effects happening on large scales is because once things have entered these two superpositions of these branches, then it's very difficult to get those branches to then interfere again. It is possible in theory to get those branches to interfere again, and we'll see that in the thought experiment I'll explain later about observers. But yeah, that's the idea, is that we get this emergence of these fixed branches. So yeah, thanks for the questions. And it's also fun to mention that states like this are sometimes referred to as cat states, because they are like, inspired by this Schrödinger's cat thought experiment, and they're quite useful for quantum computing various things. Cool. So the way I like to imagine decoherence visually is using an analogy of dominoes. So if you imagine having set up all your dominoes and then you knock one down and it does this chain reaction of knocking them all down, I imagine decoherence a bit like that. So I look inside my box, and then once I've seen a certain outcome, it's almost like it knocks over all the dominoes of the rest of my environment and puts everything in my environment into having seen the same outcome that I saw. So it fixes everything into my branch of what I saw. And another thing to mention is that if we now just, after this process has happened, all this decoherence with the environment, if we now just look at the state of the atom and the cat and the observer, say, then they behave exactly as if they're not in, if instead of being in a superposition, we replace them with just randomly being, let's say, randomly having seen the cat dead or alive. Essentially, there's no difference between a superposition and a mixture once you've interacted with the environment. So what I mean by that is, usually we care a lot about whether something is really in a quantum superposition of 0 and 1, say, or if there's just a random 50% chance of being 0 or 1. Like, they're very different. So we have superpositions, and then we have mixtures, and mixtures are these random 0s or 1s. Superposition is this actual state of being both at once. And what I'm saying here is, they are in this big entangled state. Everything is actually in this superposition of these two branches. But if we just look at some subsystem in that, if we just look at this box and we look at the cat, then it'll be exactly the same as if we just randomly had the cat alive or dead, just 50-50 chance. So it kind of behaves, this is where we can see that it behaves in a classical, in a way that's indistinguishable from being classical, because it nice connection with quantum computing, because this is exactly the problem with quantum computing, is that you get one thing interacting with you from your environment. It makes you behave like a mix of the thing control. So yeah, this is very fundamental problem with for quantum technologies. So yeah, before I move on to yeah, it says the connection is not great. Can people hear me okay now? I did get a notification on here that the
Yes.
connection wasn't very good.
Yeah,
but
we can hear you now.
yeah.
Thank you.
Okay. Yeah. Okay. Yeah, hopefully it holds up. Otherwise I can try a switch to a different yeah. Okay. Cool. Yeah, if it gets bad again, let me know, and I'll see if I can switch where I'm getting the internet from. Yeah, any questions on Schrödinger's cat and decoherence before we move on? I mean, the general themes will come up in the next thought experiments as well, but any about this, about what I've said here? Okay, maybe we can move on then to the double slit, and yeah, the concepts will come up again. So hi, yeah, not sure what happened again, but I can get the presentation back. Okay, cool. So yeah, double slit. Let's see. Yeah, the idea is that we have this barrier which has two slits, and we have a screen, and we want to send single yeah, we're going to send particles of light through this screen. So what do we expect to happen? Well, if we send something that's like a classical wave through a double slit, then what we'll see is this these fringes on this intensity pattern on the screen, where we see the evidence of having this constructive interference between the waves and destructive interference between the waves. So we get this repeated pattern of maxima and minima depending on the constructive and destructive interference. Now, if we instead sent classical particles through the double slit one by one, then we know that they would either go through one slit or the other slit. And so the intensity pattern is just two peaks, one aligned with each slit. Now, the weird thing is that with quantum particles, so say a single photon, but also single electron or anything that you have enough control over to isolate and measure, when we send that through the double slit, then it goes through and then we measure where it lands at the end, and we can build up this distribution of where we detected these single particles or single photons. And strangely, we see that there's this interference pattern where we have these different peaks in intensity, even though all we did was send a single particle through. So this is evidence of the single particle somehow must have gone through both slits, interfered with itself, and then that interference has led to higher probability of being detected at the places where there was constructive interference with itself and low probability of being detected when there was destructive interference with itself. So we see that these single particles seem to behave as waves. But there's an extra twist that if we could consider adding a detector to see where these particles are going, because this seems weird, right? How is the particle going through both at once? Well, what if we detect? What are we gonna see now? And so you can, so this is the normal double slit pattern, add a detector, and then what we see is that it behaves as though the particles just went through one of the slits each time and didn't interfere with themselves. So they behave like classical particles. So it's we just get this intensity pattern aligned with each slit. So the standard narrative around this is quite strange because so the idea is to show this wave particle duality of quantum particles. So we say without the observer, without a detector, it behaves as a wave, and with a detector, it behaves as a particle. And it seems strange that we have this. There's a kind of weird role of this detector because it's like, well, why does it stop? Why does it behave as a particle when I look at which slit it goes through? How am I as an observer affecting this this system? Like what's happening there? So I find it nice to map the kind of outcomes happening here onto this interferometer setting that we looked at before with the bond tester, and then to map the interferometer onto quantum gates on a quantum circuit. So for me, I find this helpful to understand what's going on, and hopefully it's helpful for you as well. So let me see if I can explain how we go from this double slit setting to the interferometer and see the same outcomes in this way. So we have our source of single photons, just like the double slit. Here we have our first beam splitter, which puts them in superposition. So this is, this is like putting it through the two slits, so it can now interfere with itself. So we have this superposition. It's like it's gone down both slits. And then we have this second beam splitter is where we get this interference with itself. So when our photon interferes with itself, it gets detected always at this detector because we had this constructive interference. So a click here is a signature of having successfully interfered with itself. And that's what we see on this quantum circuit. I have a photon qubit. To start with, it's 0 in single state. It enters this superposition with the first Hadamard beam splitter. Second one sends it back to the 0 state, and that's the interference with itself is this second Hadamard. And then we can measure to check that it was actually at this detector. So now let's think about what happens when we introduce this detector in the middle to see which slit it went through. So looking at this interferometer version, looking at which slit it went through is equivalent to looking at which pathway it took through this interferometer. So did it take the bottom path or the top path? Did it go up or down? So let's imagine we put a detector here and it detects up. Well, what this does is, just like with the bomb tester, it does this measurement. So in order to detect that it goes up, we do this measurement, which collapses it or projects it into only going down the top path. And then when it reaches this beam splitter, it has equal chance of going through both detectors because it doesn't have its other bit to interfere with now. So we can see that adding this detector to measure which pathway it goes through is destroying its ability to interfere with itself because it's projecting us into just one pathway. And that's what happens in this quantum circuit. We've added this measurement in between the Hadamard gates. in between our beam splitters, and then when you do this measurement at the end, you'll see that it now has a 50-50 chance of getting 0 and 1 instead of always being 0. So this is, yeah, the case of putting this this observer in this detector, seeing which path it went through. Now, what I find, so yeah, we have these two options of going up or down. Both cases, it'll destroy the interference and make an even split of the detectors. So yeah, mapping this onto the double slit, this is the outcome where you'd get those particle-like behavior of just the two intensity patterns. But what I find particularly clarifying.
Let me ask a question, because last time you said you can loop around and make it more and more less sensitive, right? That we not destroy the bomb. Can we not do the same? The you know, for that the bomb detonated to 50%, we made it.
Yeah.
Yes.
Yeah. Yeah. So if you, yeah, you could do, yeah, you can basically think of, yeah, this detector exactly maps onto the bomb. Like the bomb was basically behaving as a detector. So we could do the bomb setup with a detector instead, and we could do that version with the 100% up to 100% effective version. We could do that with a detector instead of a bomb. So yeah, it would.
We just measured the top slit. I just wonder if we get less sensitive and still can measure. I know
Wouldn't
that
there be two bombs though? Or because I see two detectors, so wouldn't that be like two bombs?
Yeah, but you would know if it not goes through the upper slit, then
Yeah,
it has to go to the down slit.
Yeah,
so
it would be two
the
bombs,
thing that's a
wouldn't it?
bit. Sorry, did someone say something?
Yeah, I said it would be two bombs, wouldn't it? Down, it would be two there, right?
So, well, one thing is that really we only need one of these because, so I put two kind of for clarity, but even if you just measure, you just put the detector in one path, it automatically tells you if the photon went down the other path, because if I put the detector here and I don't get a signal, then it tells me that it went down here. So the second detector is kind of redundant in a way, in terms of what it does to the photon. But an aspect which comes into play when you start to think about the experiment is whether it actually ends up absorbing the photon or whether it lets it carry on. And so these detectors that I've drawn with this loop is kind of assuming we figured out a way to detect the signal of the photon going past without actually destroying it, which needs some clever ways to do it and is a bit different to a bomb situation where it would absorb that photon. But yeah, I mean, the bomb tester setup was kind of different in the sense that what we were trying to look for was doing this interaction-free measurement. We were trying to detect the presence of an object here without it absorbing the photon. So yeah, I mean, it's exactly the same kind of underlying principles involved with the entanglement, the detection, and everything, but it doesn't exactly map onto the double slit in terms of the logic of what it's testing for. But yeah, so you can probably
see it now.
Yeah.
Thank you. Yeah, it was just going through my mind. But thank you very much for the detailed explanation.
Yeah, I mean, it's an interesting point to think about because I've said, okay, we can translate the double slit to this interferometer. It's interesting to think about what this quantum Zener effect interferometer with all the beam splitters, what that would, or with the looping round, what that would translate back to in terms of the more, double slit context. Is a kind of, it's an interesting question. I'll probably think about that a bit. But yeah. Cool. And yeah, so what I find interesting to think about is now, all right, so I've said I have this detector that measures this qubit. And I've kind of treated this as some macroscopic classical device that just tells me 0 or 1 for sure in a irreversible measurement kind of way. But what if it wasn't this big macroscopic observer? What if it was just a single qubit, and I just use a single qubit to detect which path my photon goes down? So if it goes down the top path, I'm going to have this this single qubit will switch to 0. If it goes down the bottom path, my single qubit will switch to a 1. And so I'm just using this one single qubit as my detector. Will I see the photon qubit behaving in this wave-like way, or will I see it behaving in the particle-like way? So will this single qubit detector stop my interference of the photon with itself? Will it stop its quantum properties, or can it still have its quantum properties because I have this single qubit detector instead of a big macroscopic detector? So maybe just for fun, we could do a show of hands of which side people think it might end up on. So can just do a quick vote of maybe, yeah, I'll ask you to use the raise hand feature first for whether you think it's going to behave in the wave way, and second if it will decohere and behave in the particle way. So hands up if you think it'll go the wave way, if we'll still see the interference. Okay, we have a handful. And hands up if you vote the particle way, that it will destroy the coherence. Okay, thanks for voting. So yeah, we have interesting distribution, more on the wave side. So it'll actually behave in the particle way. It will actually decohere the photon, even just having a single qubit detector. So the reason for this is very similar to how I said before, that the measurement can be exactly modeled by this control NOT gate. So here I have 2 quantum circuits. This one is where I've represented this classical detector just by usual measurement operation that we put in our quantum circuit. And we know that this will stop our Hadamard's from making this nice 0 at the end. It'll randomize at the end, and we'll see 0 or 1 randomly at the end, which shows that it's decohered. Now, if I put this C0 here, what it does to the photon qubit is exactly the same as what happened with this measurement operation. So it gets it entangled with this single qubit, and then when I measure my photon qubit, it's randomly 0 or 1. So because it becomes entangled with something from the outside, and then I kind of forget about that qubit and I just measure my photon, then my photon acts as if it's classical. It's not, it doesn't interfere with itself anymore. And this is what I find really enlightening about this quantum circuit way of looking at it, is that it really emphasizes that the double slit, the weirdness of the observer in the double slit experiment isn't about having this large classical seeming device measuring which path the photon goes down. If the photon interacts with even a single qubit, a single tiny quantum system that stores that information about whether it went through one path or the other path, and then we look at what happens to the photon on the screen or in our interferometer, it'll behave as though it's decohered. It'll be exactly the same as if there was a measurement. It'll be behaving in this particle-like way. So even a single qubit will cause this decoherence and this particle-like behavior. And this is exactly the problem with quantum computing. This is why quantum computing is so difficult, is that we're trying to preserve this superposition in it's like the photon qubit. You can imagine, let's say that's all of our qubits in our quantum computer that we're trying to use. They're storing our useful information. And then we just get this one particle comes from the outside, interacts with one of our qubits, stores information about its state, and then that destroys our computation because it puts it into it makes it start behaving classically, like it destroys the ability of these qubits to interfere with themselves because they've been decohered by just this one atom from the outside having interacted. So this is exactly why qubits are so sensitive to their environment, because even this tiny influence from the environment can stop them behaving in this quantum way. And I also wanted to mention that it's not that every interaction between the photon qubit and some external system would cause this decoherence. There are some interactions that won't cause this decoherence. For example, there's another quantum gate. I don't know if you've come across it, but it's a control Z gate doing exactly the same as control X, but instead of applying X or not, it applies the Z gate or not. And if you do the maths, you see that this gate, it doesn't decohere the photon. So we still get 0 every time at the end. And that's because it doesn't kind of copy over the information of the photon's qubit state onto this qubit in the way that the C0 does. So not every single interaction has to cause this decoherence, but the C0 is kind of the model for how it will cause this decoherence. So yeah, that's the kind of the conclusion of the double slit part, is that this single photon detector, single particle detector. So we have a comment about flipping the phase if the computational basis is 1, which is right. So yeah, so the control Z gate does affect the qubit, the outside qubit, but because it doesn't transfer the pathway information, that's the aspect which means that it doesn't decohere the photon's kind of pathway, its ability to interfere with itself. So yeah, it's all about what information is actually transferred over by this interaction, and this becomes very important in quantum computing, because one of the big things that you try and do to combat decoherence is to try and kind of measure your system in a way that you can extract information. You try and extract the information, certain information that you want, without destroying the information of the computation. So there's a question.
Is there a thing
about
like partial decoherence? Is there anything like partial decoherence where only like some part of the qubit collapses to the classical version, whereas the rest of it is still quantum?
Yes, I'm not sure if it's exactly what you have in mind, but you can imagine instead of a control NOT gate doing a kind of controlled X rotation with having the X rotation only being, so almost being a very fractional part of an entire NOT gate. So then you could kind of slightly decohere your photon qubit if this was a kind of very weak C0 in a way, and that would be equivalent to having this complete C0 is like you've dumped a load of noise onto your qubit. You've basically just randomized it. So this is telling you nothing now, it's just random. If you had this kind of weak C0 interaction with the environment or with your detector, with your outside system, then it would be like adding a little bit of noise to this qubit that has decohered. So it'll be like it decoheres a little bit. So you can, yeah, the decoherence can be, it could be worst case, just completely random, or it could be there's a little bit of noise. And that's what we see in when we do experiments. What the people in building the quantum computers are trying to do is get that decoherence as small as possible. Yeah, so a slight rotation would be a way of implementing. Yeah, that's what I mean when I say a weak C0. I'm kind of imagining a control over small rotation to kind of transfer a bit of information, but not the full thing. And yeah, then there's a question. So the quantum path detector cannot be in a superposition. So it can be in a superposition. And if you look at the overall system of the photon and the detector, then together, at this point, they will be in this entangled state. They'll be in an entangled superposition together. And if we retained, so if we wanted to, we could, if we had control over this qubit, this path detector, we could put another C0 to undo this one. So we could undo this interaction between our qubit and our photon, and then do this Hadamard, and then everything is fine. It's not decohered anymore. But if we do this measurement and then forget about our quantum path detector, we say we don't have access to that anymore, then it will cause this decoherence. So it could be undone after being done. You could do the C0, you could undo it, but then it's not really detected it anymore, right? Because you'll have erased its ability to have done the detection.
So
And
just as
yeah.
a reminder that you said that you need to go exactly as at 3. It's just 2 minutes or 1 minute before 3.
Yeah. Yeah. I mean, I could. Yeah, I could.
We still have
potentially
we have another lecture next week, and hopefully we'll be in better shape at that time, because they changed some certificates for the networking here. I think we could stop here, and then at least we have it recorded, and then we'll pick up next week and wrap it up.
Yeah, sounds good. Yeah, I'll leave the many worlds test one for next week. Maybe I can just briefly respond to the questions here.
Yeah.
There's one. Does this mean that there's a connection between non-commutativity of mathematical formalisms we use to model these pathways, phenomena, and the paradoxes? Do you mind clarifying what you mean about the non-commutativity of the mathematical formalisms?
Yeah. So, like, in the context of, I guess, Lie algebras and sort of using operators to handle observables, there are like specific like commutativity relations that happen there. Is that something that we might expect to influence the certain paradoxes that we find?
Yeah. Yeah, so there's this kind of, that's at the root of the Heisenberg's uncertainty principle situation of if you do the X basis measurement and a Z basis measurement, then they don't commute, and not taking that into account properly leads to certain paradoxes. I don't think it kind of comes out from these ones, but there are other ones, like there's one called Hardy's paradox, which is very much that situation. Yeah, I will need to leave now, but yeah, I could expand on that next time. And also, yes, you can decohere if you retain quantum control over your detector, to answer the other question. So yeah, let's pick this up next time. Please keep the questions coming. You can send me them offline after today as well if you want, and then I can respond next week. And yeah.
And so
Uh,
thank you very much, and thank everybody for their patience. And as I said, maybe next time we're going to be in better shape. Thank you once again.
Okay,
right.
cool.
We'll see you
Bye,
in a
everyone.
week. We'll see you in a week. Bye-bye.
Bye.